from here, we take a leap and move to the physical foundation of biochemistry. We are moving to the physical foundation of biochemistry. We are going to look at how energy is gotten, the economics of energy within the cell. What are the factors that makes a reaction feasible in a cell? So let's get rolling. Biochemistry has the task of studying quantitatively and chemically. We study quantitatively and we also study chemically the means by which living cell extract, produce, channel, distribute, and use energy. I'll go through that again. In physical under the physical foundation of biochemistry, we have the duty of studying quantitatively and chemically the means by which living organisms extract, produce, channel, distribute, and use energy. So we are only looking at energy economics and reaction feasibility when we are looking at the physical foundation of biochemistry. So energy and its conversion in the cell can be studied in the concept and idea of thermodynamics law. So under physical biochemistry, you'll be looking a lot about on physical laws, the rule of enthalpy, the rule of entropy, free energy change, and the like. So let's get going. The physical ideologies of biochemistry are hinged on the following facts. One, living organisms exist in a dynamic but steady state, which is never in equilibrium with its environment. This is what we are trying to say. Okay. Living organisms, when I say something is dynamic, it means it's changing constantly. It's changing constantly. And when I say it is steady, it means on an average, it is constant. Are we together? Now, living organisms are in dynamic, steady states. Living organisms are in dynamic, steady states with environments. What do we mean? If I look at a living entity or a living cell, now a living cell is a system on its own. When we're looking at system under physical science, a system can either be a closed system, an open system, or an isolated system. Now, isolated system is that which does not exchange both energy and matter. Isolated system does not exchange both energy and matter with its environment. The system is just on its own. It is well proven. It is well secluded from its environment. There's no transfer of energy. There's no transfer of matter. Now, open system is one in which there is transfer of both energy and matter with its environment. Open system transfers both energy and matter between itself and its environment. It transfers both energy and matter. Now, closed system. A closed system transfers energy but does not transfer matter. I go through that again. Closed system transfers energy to and fro its environment but does not transfer matter. Now, the living cell is an open system because the living cell transfers both energy and matter with its environment. The living cell, on most occasions, is not in equilibrium with its environment. For instance, would you assume that the same composition around me is what comprise of the composition within me? That's never possible, because within me I have blood, my intestine, everything thoroughly regulated by homeostasis. Now there's no homeostasis to regulate the atmosphere, right? So my internal environment can never be in equilibrium with my external environment. Of course, that's true. So what will now happen is that despite the fact that my internal environment in a cell is not in equilibrium with the external environment, there is an exchange of both energy and matter. Now, the exchange of both energy and matter is dynamic and steady, because this is what we are trying to say. For instance, inside your body, you have glucose. Let me use blood glucose as an example. Blood glucose. Now, constantly, glucose is being consumed in your body. Constantly, glucose is consumed. Now, despite the fact that glucose is consumed constantly means glucose in your blood is dynamic. Are we together? The fact that glucose is consumed constantly every time is the fact that measures on the fact that glucose is dynamic. The more you act, the more glucose will be consumed. In fact, if you are in a lying position, you are still using glucose, because our brain uses majorly glucose as the source of fuel. There are other tissues in our body. For instance, the retina uses glucose majorly as the source of fuel. So either you are sitting or walking, glucose is constantly being consumed. Now, despite the fact that glucose is constantly being consumed in your body, your blood glucose level is always fairly constant. Yet is always fairly constant, which means this gives us the fact that glucose in your body is dynamic. Now, this gives a fact that glucose in your body is steady, which means there is continuous intake and outflow of glucose. Despite the fact that there is continuous intake and outflow of glucose, for instance, you always consume food, you consume carbohydrates to get your body supplied with sufficient glucose. The fact that you get your body loaded with glucose, yet that is going to make your blood glucose level is going to make it at its peak. But despite the fact, your blood glucose will still remain constant. Why? Because there are regulations. There are typical regulations. So the point I'm trying to drive home is that biomolecules, not only glucose now, biomolecules in cell are dynamic, which means constantly biomolecules are being produced and constantly biomolecules are being degraded in a cell. I'll go through that again. Day in, day out, constantly biomolecules are being produced in a cell. Also, day in, day out, biomolecules are being degraded. Now, the fact that the rate of synthesis of biomolecule and the rate of degradation is now being regulated such that they balance each other to give us a steady state. I'll go through that again. The rate of influx and efflux or synthesis and degradation, which is the dynamics of biomolecule in the cell, is monitored and regulated such that the average amount of biomolecules in the cell is fairly constant. Are we together? So you won't say you are having you are having low blood glucose. You won't say you are having low blood glucose because your body is constantly degrading glucose. No. You are always also eating glucose. There is gluconeogenesis in your body, which helps even to produce more glucose, even when you are not consuming glucose. So the body just looks for a way to make biomolecule rate or biomolecule concentration, in the living entity steady, despite the fact that the biomolecule is always dynamic, always producing new one and degrading old one. So note that fact that living organism exists in a dynamic but steady state, which is never in equilibrium with its environment. So I just explained that point very well. Now another thing is that organisms transform energy and matter from their environment. Organisms has the ability and capacity to transform energy and matter from their. For instance, look at photoautotrophs. Photoautotrophs. Now, photoautotrophs will trap sunlight energy. Now, it's now going to use that sunlight energy it's trapped. It's going to use it to split the molecule of water. That's the light phase of your photosynthesis. That's rudimentary in biology. You have your glucose synthesis, in which you have your redox reaction that forms your glucose. Now, what I'm trying to say is that organisms has the ability to harness energy from the environment. So your plants has the ability to harness the sunlight energy and use that energy for itself, the production of sugar, the production of glucose. So living organism has the ability to feasibly trap energy and use that energy for its own. Now, another thing is that the flow of electron provides energy used for cellular work done. The flow of energy, the flow of electron flow provides energy okay, so electron flow provides energy which the cell used to do its work. Now, this is what I'm trying to say. All the activity in a cell, be it growth, reproduction, sensing its environment, virtually all activity in the cell requires a cellular energy, requires energy. Now, this energy, where will the cell get it from? The cell will get it from more or less redox reaction. Now, that is what I explained here earlier on. Now, water here, for instance, in photoautotrophs, for photosynthesis, I have water, which is splitted by sunlight to H plus OH minus. Now, the hydrogen here is now used to reduce carbon dioxide. The hydrogen released here is used to reduce carbon dioxide to sugar. So at the end of the day, I will be having in the presence of light. Now, here, the water is a balance, yeah. Yeah. Now, the water here is splitted. Now, at the end of the day, all the chemical reaction that occur here to drive this reaction is occurring as a result of splitting water here. Now, the electron from the splitted water is now passed down to CO2 such that sugar is produced and my OH is reoxidized back to oxygen. Now, that corroborates the fact that water is splitted here. Now, the hydrogen is used as electron to now drive the reduction of carbon 4 oxide to sugar. So, another thing that we have to explain and know here is that most cellular reactions are energetically unfavorable. Yeah, most cellular reactions are energetically non-favorable, but they are driven by energy coupling. This is what we are trying to say here. In a cell, for instance, let me look at the first step in glycolysis. Now, the first cell in glycolysis would have normally occurred this way: glucose plus Pi to give me glucose plus inorganic phosphates to give me glucose 6-phosphate. But in a cell, this reaction is not feasible because this reaction has a large positive free energy change. It has a large therefore this reaction is not spontaneous. This reaction is not spontaneous. So what will occur? The fact that this reaction is not spontaneous does not mean my body will stop using glucose. This reaction is endagonic. Now, because instead of it yielding energy, instead of it to focus on creating more energy, it is rather giving a large positive free energy change. Instead of it to give me a free energy, it is rather consuming my free energy. So what will my body do? My body will still need glucose 6-phosphate to continue glycolysis. So what the body will do is this: the body will now incorporate endagonic reaction, which is not feasible. The body will now incorporate it with hexagonic reaction, which has large negative free energy change. I'll go through that again. This non-spontaneous reaction, as a result of large positive free energy change, will be incorporated. That's where biocoupling comes into place. Bioenergetics coupling, that's where it comes into place. This reaction that is not feasible will now be coupled with another reaction that has large negative free energy change. Now, the excess large negative free energy change will now be used to drive my previously non-spontaneous reaction to spontaneity. I'll go through that again. The free energy that my reaction that is having large negative free energy change is having, the free energy it's having, I will now use it to drive my previously non-spontaneous reaction to spontaneity. Now, what do I mean? Look at this. For me to drive this, the reaction I will use is this ATP split into ADP plus inorganic phosphate. My ATP here means adenosine triphosphate. My ADP here means adenosine diphosphate. My PI here means inorganic phosphate. Now, this reaction is hexagonic. because it has large negative free energy change, a large negative delta G. Our free energy change is delta G. This is having a large positive delta G. Now, because these two reactions, they are having the same intermediate. Because before a bioenergetic coupling can occur, you must have the same intermediate, because there is the same intermediate here. Now, that means I can couple these two reactions together such that the excess hexagonic energy here can be used to drive my previously non-spontaneous reaction here to spontaneity. So the reaction will now occur, the biocoupling, the coupling of the two will occur this way. I will now have glucose plus ATP to give now, because these two are having the same intermediate. Now look at this. This is energetically favorable and it is energetically feasible, because the overall of this is still going to have a negative free energy change. Now, what I'm trying to say in essence is that more often than not, biochemical reactions in the cell are not feasible because they require large energy to drive them, because the reactions, the biochemical reactions themselves are having large free energy change. Maybe I should define what free energy change is. The free energy change is the potential energy a chemical system possesses to perform a work. I'll go through that again. Free energy change is the potential energy that a chemical system possesses to perform a work. So in biomolecular reaction, my straightaway reactions is usually non-spontaneous because the free energy change is large and it is positive. It's positively large. And the rule of spontaneity of reaction is this: for any reaction to be spontaneous, the free energy change has to be negative. That's the rule for spontaneous reaction. So since this is positive and it's even large, so this cannot occur. So for this to occur, what will happen is that this will now be incorporated with another reaction that is hexagonic, having large negative free energy change. Of course, the negativity here must be such that it can overpower the positivity here, such that the overall reaction will still be negative. Therefore, now, my ATP here, the hydrolysis of my ATP, we call this the hydrolysis of phosphoanhydride bonds. Now, the hydrolysis of my ATP here is going to yield large energy, large negative free energy change, large negative delta G here. Now, the large negative free energy here can now be coupled to my previously non-spontaneous reaction. Why? Because of the presence of the same intermediate. Now, the presence of the same intermediate now gives me a ground to incorporate these two together. Good. Now, by the time I now incorporate these two together, I will now be having glucose. Instead of having it plus inorganic phosphates, first of all, no, because that's not feasible, not spontaneous. So I will now be doing my glucose plus ATP here to give me my glucose 6-phosphate, the products which I need, plus my adenosine diphosphate. Overall reaction, which is negative free energy change. So because of this fact, my reaction through this pathway or through this scheme is feasible, despite the fact that the initial scheme is not feasible. So I can drive this to feasibility by coupling it with another more energetic reaction. So in a lot of time, our cell perform this type of biocoupling because most reaction in the cell is non-spontaneous, so it couples it with energy yielding reaction, such that the overall reaction now becomes energetic, such that it is having negative free energy change. So there are things I have to mention: the rule of spontaneity and randomness, that's entropy. Now you notice that the first rule of thermodynamics states thus that energy can neither be created nor destroyed, but can be converted from one form to the other. Good. We explained that when we said our living cell is a open system which exchanges both energy and matter from it exchanges both energy and matter it exchanges both energy and matter with its environment, and it transforms that energy. For instance, in photosynthesis, the light energy which is trapped from sunlight is transferred or is transformed, to chemical energy which it uses to split water and uses the hydrogen to reduce carbon dioxide to glucose. Now, the second law of thermodynamics states that the tendency in nature of a system, the natural tendency of a system is towards an ever-increasing entropy. Now, what is entropy? Entropy is the rate, entropy is the degree of randomness or disorderliness of a reaction or of a system. The degree of disorderliness or the degree of randomness of a system is what we call entropy. So, in nature, for a reaction to be spontaneous, entropy must increase. But notice that in a cell, entropy is reducing. Because, for instance, you remember that I said cell must have the ability to aggregate simple molecule into macromolecule and even fold macromolecule into supramolecule. So that means I am reducing randomness. For instance, if I have 20 amino acids, they are free, they are flying everywhere. Now, if I bring those 20 amino acids in amide linkage to form a single oligopeptide, instead of me increasing entropy, rather I am decreasing entropy. I'm decreasing randomness. I'm decreasing disorderliness. Now, if I even bring that oligopeptide and I fold it into a supramolecule, let's say an enzyme. Now, I'm even reducing randomness more, which means the reduction of randomness is against the second law of thermodynamics, which tell me that for spontaneous reaction in a system, entropy must increase. So, automatically, I have reduced entropy, which means naturally biomolecular reactions should not be feasible. That's explaining one of the reasons why this reaction here is not feasible. But for it to be feasible, and two things is the aim I want to achieve now. One, I want to achieve reduction in entropy. I want to achieve a reduction in randomness, and at the same time I want my reaction to be feasible. It's just like I'm pursuing two things that are on opposite end. The rule is that for reaction to be spontaneous, entropy must increase, but I want entropy to reduce, and at the same time reaction to be feasible. That's why I'm going to look for a more energetic reaction to drive my reaction to spontaneity, despite the fact that I am reducing entropy, or I'm reducing the degree of randomness. So that's what we do in biochemistry. Okay, now, so how do I relate entropy with free energy? How do I relate entropy with free energy? William Gibbs has given us an explanation. William Gibbs has given us an explanation of that. Now, I have entropy. I have enthalpy. Enthalpy is the heat change in a chemical system. Enthalpy. I have free energy change. And I have absolute temperature. Now, all these factors contribute to energy change. All these 4 factors contribute to a reaction spontaneity, and they are related by the formula given by Willard Gibbs, known as the Gibbs thermodynamics equation, known as delta G equals delta H minus T delta S, where my delta G is my free energy change. I defined free energy change earlier on as the potential energy which a chemical system possesses to do work. Okay, my enthalpy, that is the heat energy change in a chemical system. My T is my absolute temperature. Absolute temperature means your degree of temperature in Kelvin. So if you are having your temperature in degrees Celsius, you have to convert to Kelvin. And my delta S here is talking about entropy. It's talking about entropy. So if I know the entropy of a reaction, and I know the absolute temperature of a reaction, and I know the enthalpy of a reaction, I can calculate its free energy change by this formula, which relates enthalpy, which relates free energy change to enthalpy, absolute temperature, and entropy. So by that, I have explained quite a lot of things when it comes to knowing how feasible a reaction will be, knowing how energy will be gotten from the environment, how energy will be transformed from the environment, knowing that, okay, naturally biomolecular reactions in the cell, biochemical reactions in the cell are not feasible. Why? Because in biochemical reaction, instead of you to increase entropy, you are rather decreasing entropy. Okay? Now, instead of that to affect this, which it will, but I don't want it to affect, so I will biocouple the reaction. I will couple the reaction with a more energetic one, just like I've done here when I coupled my glucose with adenosine triphosphate to yield my adenosine diphosphate and glucose 6-phosphate, which is the product that I need. So this is a quantitative factor or a quantitative measure, a quantitative measure of reaction spontaneity, a quantitative measure. It's a quantitative measure of reaction spontaneity, especially in biochemistry in a cell. We are talking about this, so if I want to know if a reaction will be spontaneous in a cell, this formula gives it to me. So apart from this, there is another formula that can tell me the spontaneity of a reaction, and that is my equilibrium constant. Equilibrium constant. For instance, if I have a reaction in this way, A plus B to give me C plus D. Now, you know that I have my equilibrium constant to be the concentration of product all over the concentration of reactant. So my KEQ here will be the concentration of my C multiply the concentration of my D all over the concentration of my A multiplied by the concentration of my B. So this in relation or in addition to this gives me the quantitative measure of a reaction spontaneity. So here, when I have a large KEQ, when I have a large KEQ, it's telling me that my reaction is feasible. But when I'm having a low KEQ, it means my reaction is not feasible. And so I go through that again, that large positive equilibrium constant KEQ means my reaction is feasible. The reaction will continue until all my reactant is consumed. But a small KEQ shows a reduction in the feasibility of a reaction. So we proceed from there, that these two equilibrium constants, these two measure of reaction spontaneity can be matched into one. That's when you have specific, that's when you're talking about specific standard free energy change. Now your specific standard free energy change is a constant value, that is specific for each reaction, a constant value specific for each reaction. So that's where you're talking about your specific free energy change. So let's relate this to this and look at the third way by which we can evaluate reaction spontaneously, so reaction spontaneity arithmetically, pardon me. Okay. That's because we are relating the two together. You now have delta okay. For reaction, we are saying for the reaction that goes this way, that's A plus B, C plus D. So that will be ln natural logarithm of C now. From this place, I have my Gibbs free energy equals to specific free energy plus this is the rare gas constant, a value which is known as 8.315, yeah, 8.315 joule per mole Kelvin, where your G delta G equals free energy delta G naught equals specific energy, then R equals to gas constant having a value of 8.315 joule per mole Kelvin. Then my T equals absolute temperature in Kelvin. Okay, and the ln here means natural logarithm. That is 2.303 of the logarithm to base 10. Okay, now having known that, then I have it here that then my delta G equals delta G naught plus R T ln. Now you recall that this You recall this that we got earlier on. You now recall that that's the same thing we have here. So I can say ln of Q. Now, at equilibrium, notice the equilibrium here. At equilibrium, our delta G, which is the free energy change, equals 0. Then I can say 0 equals delta G naught, which is my specific free energy change, which is specific for a particular reaction, plus RT ln KQ, equilibrium constant. Then I can say my equals to negative RT. Now you recall that ln x equals to 2.303 log to base 10x. Then I have delta G naught equals minus 2.303 RT log to base 10 of KQ. So, looking at it from this point, it is crystal clear that I can relate my free specific Gibbs free energy change with the equilibrium constant. So initially I said the measure of reaction spontaneity will be Gibbs free energy change and the equilibrium constant. Now I have a third one to it, which is the specific free energy change, which is related directly to the equilibrium constant, especially when it is at equilibrium. Okay, so having explained this, let's move forward in explaining our physical foundation of biochemistry, talking about the spontaneity and the factors that affect how a reaction will proceed. Another thing we have to mention there is that cellular reactions require biocatalysts. Now I said earlier on that biochemical reaction is somehow working against the thermodynamics second law. Thermodynamics second law is telling us that for reactions to proceed, entropy must increase, but in biochemical reaction we are working against entropy because we are creating more orderliness. You remember while I was saying that I explained amino acid getting complexed together, getting aggregated together to form protein folding to form supramolecules, thereby reducing orderliness down the way. Okay, so having said that, that reaction that reduces entropy, that reduces disorderliness, it is not thermodynamically favorable, and that's the reason I said earlier on that such reaction is not thermodynamically favorable, and it has positive large free energy change. Okay, so and I said for such reaction to occur, you need to couple such reaction with another reaction that has a large negative free energy change, so that the excess hexagonic energy from that second reaction having a negative free energy change will be used, the excess energy from there will be used to drive the initially non-spontaneous reaction to spontaneity. Now, apart from using a hexagonic energy, apart from using the free energy from a highly hexagonic reaction to drive biochemical reaction against the wish of thermodynamics second law, there is also the need of enzyme as biocatalyst. The truth of the matter is that in the absence of catalyst, most reaction in the cell will take years to occur. Ordinarily, glucose getting converted to glucose 6-phosphate will have occurred for like a long period of time for such reaction to move to completion. But with the presence of enzymes, which are organic catalysts, enzymes are organic biocatalysts that help to speed up the rate of biochemical reaction. So with the presence of catalysts, such reaction that should have taken like forever just occur within little space of time, within little range of time. So let's look at enzyme, because for biochemical reactions to proceed and for biochemical reactions to be feasible, more often than not, you need a biocatalyst, which is more often than not an enzyme. So like I said earlier on, enzymes, they are more or less proteinous in nature. They just tend to make your reaction happen faster. So what are the mechanisms by which your enzymes act to speed up your rate of reaction? There are majorly two ways. The first is that enzyme is going to create a more feasible, a more favorable transition pathway for the reaction to occur. The reason, the point I'm trying to explain is that enzymatically, before your substrate is converted to product, in between here you have a transition intermediate. Now, the transition intermediate is just like the transition molecule, that the intermediate molecule between your substrate, that is your substrate, and your product before it gets converted to your final product. And what your enzyme will do is that it is going to create a more favorable and it's going to create an easier pathway for this transition intermediate to form. How? It is going to lower the activation energy. You remember the energy profile. You remember energy profile. The second mechanism by which enzyme achieve this feat of speeding up the rate of biochemical reaction in the cell is because the binding of transition intermediate to enzymes will help to create exergonic energy, will create free energy that the chemical system will use to speed up its reaction. What I'm trying to say in essence is that binding of transition intermediate, I gave an illustration that substrate, for substrate to get converted to product, you have a transition. In between, you have a transition intermediate, and you have your enzyme functioning here. So I said in between here you have your transition intermediate. So your transition intermediate is just like your intermediary between your the intermediary form between your substrate and your product. So I said, as the enzyme binds the transition intermediate, it's going to create a free energy. It's going to create a free energy. During this state, free energy are created. That is free delta G, which of course is going to be negative, because I said earlier on that for a reaction to be spontaneous, delta G must be negative, and I think I've defined delta G, which is the Gibbs free energy change. Alright, so enzyme will bind to the transition state, and it's going to yield, the binding of enzyme to the transition state will yield free energy, and the cell will then use the free energy to drive this reaction to spontaneity, or it will use it to drive it in such a spontaneous, in such a favorable manner. All right, so let's look at few things about the nature of enzyme. Like I said, enzymes are organic. That's basic. They are catalysts. Another thing is that more often than not, enzymes are proteinous in nature. Although there are exceptions, it is not every time that our enzyme turn out to be protein. We have seen in cases such as you are going to see in your ribosomes. We have seen in cases where enzymes are RNA. Talking about our ribozymes, and know it now that enzymes more often than not are proteinous in nature, but there are exceptions in which instead of your enzyme to exhibit itself or to show itself as protein, you'll be seeing your enzyme in the form of rRNA, ribosomal RNA, and in such stances, you call your enzyme ribozymes. Another thing we have to know about enzymes is that enzymes are specific in action. I remember while I was explaining the chemical foundation of biochemistry, I said biomolecules in the cell are stereospecific. So also metabolism in the cells are stereospecific. Why? Because the enzymes that catalyzes them are stereospecific. Glucose, for instance, in your glycolysis, hexokinase that will help you to convert glucose to glucose 6-phosphate. The hexokinase will work on glucose D to give you your D-glucose 6-phosphate. So your hexokinase, which is to function on glucose D or on D-glucose, pardon me, your hexokinase that is to function on D-glucose will not function on L-glucose. Why? Because enzymes are stereospecific. They work stereospecifically. They are specific for a particular configuration of substrates. Are we together? So that's about that. There are other things that we have to know about enzymes. They do not start a reaction. Another thing is that enzymes do not affect the equilibrium of reaction. So that's about enzyme being biocatalyst required in the cell to make the biochemical reactions in the cell to be more favorable and to occur faster. The last but not the least point that we'll be mentioning under the physical foundation of biochemistry is that metabolism is regulated to balance energy economy in the cell. Let me write that down to make it clear. Metabolism is regulated to balance energy economy in the cell. All right, this is what we're trying to say. This is what I'm trying to explain here. In the cell, like I said earlier on, we have variety. We have a large, vast array of biomolecules in their large numbers. Now, despite the fact that these large numbers are produced and are also degraded in large number, like I said, don't forget I said that in our cell, a cell is an open system. There is constant inflow and outflow of both energy and matter between the cell and its environment. So that's telling us that inside the cell, we always have biomolecules being produced and we always have biomolecules being degraded. That's what metabolism is all about. Catabolism, anabolism. Catabolism breaking down, anabolism building up. So it occurs constantly in the cell. But despite the fact that this occurs on an average constant level or on an average dynamic steady rate in the cell, it is regulated such that biomolecules are only produced in the rate at which cells need them, and biomolecules are also degraded in the rate at which cell use them. This is what I'm trying to explain there. Your body at a normal physiological condition, your body should not over metabolize glucose and your body should not overproduce glucose. That's for instance, there is regulation between glycolysis and gluconeogenesis. Watch out for our lecture. Yes, I'm going to give a lecture on that. That's when I'll be explaining the topic glucose metabolism in animal. I will try and explain there how breakdown of glucose in the human body is regulated in tandem with creating new glucose or synthesis of glucose in the human cell. But for now, let's stick with this, that metabolism is regulated. Just know that the rate of creation or the rate of synthesis of metabolites and the rate of degradation of metabolites in the cell is regulated such that energy is not wasted, just to balance energy economy. The truth of the matter is that this breakdown, this creation of biomolecules requires energy. So a cell will not just be using expensive energy to create biomolecules it does not need at a time, and a cell will not be spending energy to degrade energy. It will not be spent. A cell will not be wasting time and energy to degrade biomolecule that its degradation is not necessary at that particular time. So have it at the back of your mind that metabolism. And another thing I have to explain is that the regulation of one metabolite, or the regulation of one biomolecule, to be more specific, the regulation of one biomolecule affects the other. This is what I'm trying to say. The regulation of the metabolism of a particular biomolecule will definitely affect, or will definitely have an effect on the metabolism of another biomolecule. For instance, there is a way that metabolism of lipid has effect on the metabolism of carbohydrates. For instance, the end product of your glycolysis will be pyruvate. Pyruvate will enter the pyruvate dehydrogenase multi-complex enzyme. After the degradation there, your pyruvate will give you your acetyl-CoA. Now, acetyl-CoA, being the end product of carbohydrates, happens to be the precursor, or let me put it this way to be more specific, happens to be one of the precursor of fatty acid synthesis in the human cell or in the animal cell. So that means at the point of acetyl-CoA, both glucose degradation and lipid synthesis can be regulated. This is what I'm trying to say. Glucose will break down to give acetyl-CoA. Degradation. Now, the degradation here is glycolysis and the pyruvate dehydrogenase complex reaction. Now, this acetyl-CoA here happens to be the precursor for the biosynthesis of fatty acids. So here we have synthesis. Now, at the point of acetyl-CoA here, both degradation of glucose and biosynthesis of fatty acid can be regulated. So that's what I'm trying to say the earlier time while I was saying the metabolism of one metabolite has a way of having effects on the metabolism of another biomolecule. Okay, biochemistry is interesting. It's just a way of learning. It's just a discipline that makes you learn how things interconvert within you, how the glucose you consume affects every other thing within you. For instance, how glucose you consume affects the metabolism of the protein you consume, how it affects the metabolism of the lipid inside you, cholesterol, fatty acid, triacylglycerol, and the rest. So it's a discipline that's interesting. It's just interesting. I agree with the fact that sometimes it can be tasking. It may require concentration more than a nominal course in the university. But trust me, metabolism is regulated to balance energy economy in the cell. Because of our time, let's move on with another aspect of the foundation about